So the skill you worked on over the weekend was perfecting that and getting more experience with that U substitution. We're just going to build on that. It's all going to be U substitution today. The difference is that we're going to have bounds. Okay, so all your answers from yesterday, what did they have on the end? Plus C. Why is there a plus C? Because there were no bounds to plug in. But for today, now it's going to be the same skill, but we're just going to add the bounds so that you can practice that. And what does that do? How do I work with that when I have bounds? So looking at that's the difference between what we call an indefinite versus a definite integral. An indefinite has no bounds, which means you always have plus C in your answer. A definite integral never has plus C in the answer because as you go through the process of plugging bounds in, the plus C always cancels it out with the second plus C at the end. So that's the difference. There is a little tweak to how you do it with U substitution. That's what we're going to focus on today. So I'm going to start with a pretty straightforward one, and I just want to walk you through how we change that. All right, so maybe Nick, can you identify what your gut tells you would be a good thing to pick as your U?
2x plus 1.
Okay, good choice. All right, so he's picking 2x plus 1 as his U. All right, and then we go through the same process. None of that has changed. The derivative of that is 2, and the derivative of u is du dx. So when we cross multiply, we end up with dx is 1/2 of du. So we'll be making a substitution. Back in our original, we'll be making a substitution for the u, and we'll be making a substitution for the dx. We additionally have to make a substitution for our bounds. So that's where the change comes in. Now that I have a bound here, the bound, the value of 0 is an x value. It is not a u value. We have to transform 0 into its corresponding u value. So it's like having a table or a y value that goes with it. So 0 is an x value. So the way we transform is we just take that x value and we plug it in to the position of x. So when I plug 0 in there, 2 times 0 plus 1 gives me 1. And so 0 itself becomes the value of 1 instead when I'm going to be working in u variable instead of in the x variable. And you do the same thing with your upper bound. Your upper bound used to be an x variable. It transforms. Okay, and you plug that in and it becomes something new. Think of it like the process of becoming a Christian, right? The Holy Spirit takes something old, the way you used to be, and transforms you into something different. So because we are changing this problem into u variable, this has to get transferred. All right, what will the value of the upper bound be? Yep, the value of the upper bound is going to be 2 now. All right, so there's a lot of kind of behind the scenes work that goes on before we actually do our real work. So our real work now says this is the number 1 and this is now the number 2. And I'm going to have u to the negative 3rd power because u is getting substituted in. And the dx is 1/2 of du. So that 1/2 can get pulled out as part of my antiderivative. So we're going to work with this until we get a number. The 1/2 will come out to the front, and then my antiderivative would become u raised now to what power? Negative 2, good. And then divided by negative 2 as the new power. Here's my plus c, and I have bounds of 1 to 2. So I will need to distribute before I plug in my bounds. So I'm going to take that 1/2. I'm going to clean this up a little bit before I plug in. So when I plug this in, what will be the numerator? When I distribute, I'm not plugging in. What's the numerator? I'd say I'd put my negative there. Okay. What's in the denominator? A 4 and u squared plus c. And the bounds are 1 to 2. And now I just plug my bounds in as normal. I don't have to change anything back. I'm working till I get a number. And so this will plug in. This is going to give me -1 over. And if I plug 2 in there, I'm going to get 16 as my denominator plus c. That's the first value. And then minus. And then when I plug the lower bound in, I'm going to get -1 over 4, also plus c. But because these are definite integrals, the plus c's cancel each other out. So I end up with -1/16 plus 1/4. And then I just need to go till I get a number. Definite integrals always result in a value, an actual value. So this would be -1/16 plus 4/16. I'm looking on common denominators. So 3 over 16 is my answer. So what key step doesn't happen or doesn't need to happen at the end anymore? Yeah, I don't have to change my u back anymore. It's one of the advantages of having a definite integral. You never have to change it back. You just continue and commit. Okay, just like your old self. Okay, if we use like the Holy Spirit analogy, you don't want to go back to what you were before Christ. You want to, okay, we fall back, but we wouldn't want to go back intentionally if we can help it. So you're not going to go back. Okay, stick with the commitment to the new bounds and then go until you get a value. Okay, let's try another one. Okay, Stephen, just taking a look at that a minute. Does your gut give you any idea of what you might want to choose as your u?
X squared minus 9.
Okay, so he's recognizing it's a quotient, and when it is a quotient, that denominator is always a great thing to choose. So x squared minus 9, he's identified as being his u. Okay, you want to talk me through the derivative process then on both sides?
So equals x squared minus 9. The derivative is 2x.
Good job. Okay. And then on the other side, we just have the plain old du dx. Okay, we cross multiply. Always working towards getting dx alone, so we end up with the fraction 1 over 2x times du. Now, before we do our substitution, this is where we want to pause and take a moment to remember to change the bounds. Okay, so SK, you want to change that lower bound for me?
-9.
Good job. Okay, that lower bound is now going to be -9. Okay, and then the upper one, Kaylin, how about you?
-5.
-5. Good. Okay, we're getting those simply by plugging those two values both into the value for x and then seeing what we get. All right, so now let's actually get to our work. So my integral is going from negative numbers, -9 to -5. I have x in my numerator. I have what Stephen picked as u in the denominator. And then I also am going to put in the dx, which is 1 over 2x as a fraction times the quantity du. And then I want to, okay, what reducing can I do and what constant can I pull out to the front? Okay, so is there a constant to pull out? What is it? Okay, 1/2 gets pulled out to the front. My integral is from -9 to -5. And what's left when I pull the constant out to the front is 1 over u du. And if you're not recognizing it quite yet, 1 over u is the same thing as u to the -1. And this would be the only case that a natural log would be appropriate. Again, a lot of people try and force natural logs every time they see a quotient. And that's not the case. It's only when you get to u to the negative 1. That's the only time you would have a natural log. So I'll have 1/2, and then my antiderivative bracket would be the natural log of the absolute value of u plus the constant c going from -9 to -5. These absolute values are key. They're going to change the answer if you don't have the right absolute values on there. I do not ever have to go back. I don't have to go back to x squared minus 9. I'm only looking forward now. So when I plug in, I'm going to end up with 1/2 of the natural log of the absolute value of -5, which gets plugged in first, plus c, minus 1/2 of the natural log of the absolute value of -9, plus c. If you don't have those absolute values, then you're kind of dead in the water because you can't use negative numbers in natural logs, and you try and type it into your calculator without the absolute values, and you're just going to get error, 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 error. So what we actually end up with is 1/2 of the natural log of 5 minus 1/2 of the natural log of 9. The absolute values make those things positive. Now there are several equivalent ways to write this answer long term. Because 1/2 is in common, I can write it like this, the natural log of 5 minus the natural log of 9. That would be one equivalent way to write it.
Isn't that reduced
Yeah, go ahead.
to natural log of 5 9?
Yes, okay, so the subtraction of natural logs is also another way to write this, would be the natural log of 5/9. Okay, Ethan, did you have?
Yeah, I was going to ask if that's how it works out, because if you left them negative, it would cancel out and divide them.
Yeah. All right, and another thing about natural logs is when you have a number that sits in front of the natural log, that is equivalent to the natural log of 5/9 to the fraction 1/2. And that is the natural log of the square root of 5/9. I just want you to see all those different equivalent ways to write the answer, because you may write it one way and the back of the book may have it a different way, and they are equivalent and they are the same. All of those are acceptable. Okay, the only time you're really going to have to worry about that is if it's a multiple choice and you got to find which one they wrote their form of their answer in, but those are all the same. Okay, they're all equivalent. All right, last one. Any questions on that one? We're going to finish before the bell, maybe? Okay. All right. We saw this one earlier today. Does the u jump out to you? It's a product this time. Tangent. Okay, good. So we want tangent to be our u, which works out great because the derivative of tangent is secant squared. And so we have the presence of a derivative. So cross multiply, and we'll get 1/, secant squared du. Okay, but then we got to change our bounds. Okay, my lower bound. Okay, so Julie, how about it? The lower bound, what will that become? So what am I going to do with that 0? Okay, I'm going to plug it in. And what is the tangent of 0? Still 0, right? So that one didn't change. Okay, then we have our pi/4. Okay, so Reagan, let's plug that one in. Yeah, that is 1. Good job. Okay, so now I can move forward, and my bounds are now 0 to 1. Tangent was my u. Secant squared of x. And then dx is 1/, secant squared of x. So beautiful. You can't really get much better than that. I mean, talk about an ideal integral. 0 to 1 of u du. I mean, that integral doesn't get any better than that. The bounds are about as good as you can get, and then this antiderivative is about as simple as it can be. So u squared over 2, 0 to 1. And then we plug in, and we get 1/2. 1/2 minus plus c minus 0 minus c, but 1/2.